Welcome to the deep dive. Today we're jumping into the Online Encyclopedia of Integer Sequences, the OEIS. Specifically, sequence A000306. It's listed as counting trees of diameter 8, which sounds pretty specific. Might be interesting for, number theory students.
It is quite specific, and when we say trees, we should probably clarify we're talking graph theory here.
Right, not the leafy kind.
Exactly. So, connected graphs, no cycles, think branches, but never looping back on themselves.
Okay. And diameter 8, what does that mean in this context?
The diameter is basically the longest possible path you can find between any 2 points or nodes in that tree. So diameter 8 means the longest straight shot through the tree is 8 steps, node to node. And crucially, these are unlabeled trees we're counting.
Unlabeled, meaning the structure itself is what matters, not how you label the points.
Precisely. If you can rotate it or slip it and it looks the same as another tree, we count it only once. It's about the fundamental shape, which makes counting them much trickier.
I bet. Looking at the sequence.
Yeah.
Wow, it starts 1, 4, 19, 66, 219.
Yeah, it ramps up fast.
It really does. And there's this note, offset 9, 2. What's that about? Does the 1 mean trees with 9 nodes?
Yes, exactly. The first term corresponds to trees with 9 nodes that have a diameter of 8. The offset just tells you where the sequence starts in terms of the parameter, in this case, the number of nodes. It's often just a convention for, well, mathematical neatness sometimes.
Okay, got it. So why is counting these particular trees so hard? It seems like such a defined structure.
Well, it is defined, but the number of ways to connect those nodes while sticking to the rules connected, no cycles, and that exact diameter of 8 just explodes combinatorially. It's not a simple pattern you can spot easily. This isn't just, adding numbers. It's a deep combinatorial problem.
Which explains why it's got some history, right?
Yeah.
This sequence, A000306, it was in Sloan's original 1973 handbook.
Oh, yes. And the Encyclopedia in 95. It has old identifiers, too. M3552 and 1440. Shows it's been on mathematicians' minds for a long time.
Now, people have been trying to count these for decades.
Absolutely. Johnny Olum was working on enumerating trees by height and diameter way back in 1960. That foundational work is really important here. And generating the terms, especially further out, that takes serious computational power and clever algorithms.
Like the PRI program mentioned in the OEIS entry by Christian Severs?
Exactly. That program from just May 2023 shows this is still an active area. It's a blend, you see. You need the graph theory insights, the combinatorial understanding, and the computational tools to actually calculate these numbers.
It's a living field then.
Yeah.
The OEIS entry mentions keywords too, like non-negative.
Right, standard sub.
And approved.
Okay.
And that Severs extended it up to, 4,442 terms?
He calculated the term corresponding to 400 and 442 nodes, yes. The approved status means the sequence definition is solid, it's verified, it's not just someone's random list, it's curated mathematical data.
So wrapping this up then, A000006 gives us this precise count for a very specific kind of graph, unlabeled trees with exactly 8 steps in their longest path.
That's it. It's quite elegant, really. It shows how seemingly simple rules can generate complex, rapidly growing sequences.
A snapshot of combinatorial complexity.
And it speaks to the beauty of finding these patterns in discrete structures. It makes you wonder, doesn't it? What other graph properties could we count? Diameter 9, different types of graphs. What patterns are still out there waiting in these combinatorial spaces? Something for you to think about.